will let bacteria grow dramatically. A typical example is blood agar. Blood agar is widely used in a clinical medical setting because if somebody have a coughing symptoms, sneezing, coughing, you had a sputum sample, which is we maybe thought it is Streptococcus pneumoniae. We want it to grow dramatically, then we can do some isolation identification. We need to use the blood agar. Of course, another function is to differentiate. We'll talk real quick. So, how dramatically it can grow? You're using a supported medium, might be grow 10 to the 8th, 10 to the 9th. This medium might be grow 10 to the 10th cells per ml, but no more than that. Okay, let them dramatically grow. So we're going to talk about, a good example is the blood agar. What is blood agar? This is the agar containing 5% sheep blood. And with tropic soil agar base, TSA base, which means we are making a TSA agar. We following the formula on the bottom. We dissolve in the water. At the same time, we're going to add 5% sheep blood. So the agar looks very bright red. Now, why we use 5% sheep blood? Because in 1970s, there is a research showing 5% sheep blood. The characteristics is very similar to human blood. That's why we're using sheep blood. Then, why it is an enrichment ingredients? You know, blood, there is all kinds of nutrition there, hemoglobin, all kinds of things there. That's why it is an enriched medium. Now, we're going to come up to another thing. When you look at here, chocolate agar. This is something I want to say. It's a very confusing terminology. A very confusing name. Chocolate agar, first of all, you need to know, there is no chocolate there. This is not an agar. Do you don't follow this? This is TSA agar. Oh, you put a bunch of chocolate there, then become a chocolate agar. No. Then why we call it a chocolate agar? Because it is 5% sheep blood, add TSA base, then we heat it at 70 degrees Celsius, and then the agar turn brownish color. Therefore, it looks like a chocolate. So, a chocolate agar should say chocolate-like agar. However, people think everybody is really smart, so they take this one out. But if you're amateur or you never learn about this, you see chocolate agar, you very easily think about there's chocolate there. No, it's not. It's a chocolate-like agar because it looks like the brownish color is chocolate. And then the question is, why chocolate agar is important in the clinical area? Because this used to grow fastidious bacteria. Like I just mentioned, Haemophilus influenza. Okay? We may have some sample in the lab. We could show you next Tuesday for the chocolate agar. Okay? Remember this. We will be mentioned again in examination 2 when we talk about clinical microbiology for all those human being pathogens. So that's for chocolate agar. Okay, the last one. Blood agar is also a differentiated medium. So the next question will be a differentiated medium. So what is a differentiated medium? Differentiate medium. When we talk about this differentiate, which means based on chemical or biochemical reaction, we will see color change of bacterial medium after bacterial growth. That's called a differentiated medium. Most of the time it's color change, 90% of the time. So I'm going to give you some of the examples. Let's say a Macanthi agar. Give you an example of Macanthi agar. If you grow E. coli there, it is pink pollen. If you grow Pseudomonas, it is colorless. Just an example. That's why we say it's a differentiated medium. Now, I talk about all these already. Then you think maybe it's simple. Okay, why it's difficult? Because in the real life, a median is a good combination. Most of the time is all of them. That's why it's a little bit confusing. That concept is a little bit difficult. Because most of the time is a 3 or 4 items combination, at least 2. So I'll give you an example. A Macanthi agar. We want to talk about this. What does the Macanthi agar looks like? You have seen the lab Tuesday. A very purplish color. You put E. coli there, grow like pink. Now what are the ingredients right there? Okay, the first thing I want to say. Now of course you know this is a complex medium. This is a solid medium. Is that right? This is from the other characteristics. Complex, solid, medium. You know about it. Number 2. First of all, I want to say, this is a selective medium. Why it is a selective medium? Because it looks like purple. Now why it is purple? Because it has a very important ingredient there called the crystal violet. Because there is a crystal violet as an ingredient in the Macanthi agar, so only gram-negative bacteria can survive. Then the question is why? Everybody should know. Why? Because crystal violet will attacking peptidoglycan of a gram-positive bacterial cell. So in other words, when you do the gram stain, the bacteria is dead on there, okay? Because this will attack heavy peptidoglycan of gram-positive bacteria. Now, gram-negative bacteria is very thin. That's why it's not easy for attacking. So, it's a selective medium. Only gram-positive bacteria will survive. But I tell you one thing, in the real life, it does not help too much. Because there's so many gram-negative bacteria, maybe thousands, hundreds, millions of them. Okay? But at least let's take out half of them gone. So it's a selective medium. Number 3, it is a differentiated medium. Why? Because of one of the ingredients of Mercanti agar is lactose. This is another thing, people think everybody is smart. When we have a Mercanti agar, when we talk about a Mercanti agar, anything like that, it is actually is lactose Mercanti agar. Because we think everybody knows, that's why we take this one out. So the reason is we have other bacteria, other media called sorbitol mercanti. So when you buy medium, other medium, if it's sorbitol mercanti is eroded there. If lactose mercanti, they take it off. They just say mercanti agar. But I'm going to tell you, if it's only say mercanti agar, the ingredients is lactose. If sorbitol mercanti, there's no lactose, the major ingredient sugar there is sorbitol. Why? Why lactose is important? Because some of the bacteria can go in through lactose fermentation. When they go in through lactose fermentation, generate lactic acids, it will be low down the pH of the medium because of the acid. So the pH will be decreased. Once the pH is decreased in this media, there is a pH indicator called neutral red. And this neutral red will turn pink. That's why you inoculate E. coli, it shows pink color, because E. coli fermented the lactose. Low down the pH, the neutral red as a pH indicator showing you pink color. And then why it is important? When we talk about E. coli, we are not just talking about those generic E. coli. We were talking about E. coli 0157H7. If you heard about the news, if you look at all the food safety news, after 2012, we talk about the big 6, which is called a non-0157 E. coli. They are same as risk as E. coli 0157H7. Now, how we differentiate them? We using Mercanti agar and sorbitol mercanti. Because Mercanti agar, E. coli 0157H7 is pink. On sorbitol mercanti is colorless. For big 6 non-0157 E. coli, Mercanti agar is colorless. Sorbitol mercanti is pink. Okay? Now this is, of course, we have lactose. That's why this agar is important for differentiation from the food safety standpoint. Just give you an example. Okay, so this is an example for Mercanti agar. I think I do have a question for manito salt agar in the exam questions. We're going to talk about on Thursday. Okay? This slide is important. We're going to give you another idea for differentiated media is blood agar. You're going to remember these slides right now. But we're going to talk them again in the examination too, when we talk about the bacteria passages. This is, we talk about a differentiated media example for blood agar. So when we talk about blood agar, we said it's in which media? Because most of the bacteria can grow in rich bacterial media, can grow dramatically, in the exception of fastidious bacteria. Number two, it is a differentiated media. Why? Because of hemolysis. Based on the bacteria, can complete or incomplete hydrolysis blood cell, we could differentiate them onto alpha hemolytic and beta hemolytic and gamma hemolytic. Alpha hemolytic is incomplete blood cell. Turn dark, not really dark, they say it's dark green color. I would say just green color. Beta hemolytic is complete hemolysis. So the colony is transparent. Then what is gamma hemolytic? Nothing happens. Now what is the example for alpha hemolytic? Right there. Streptococcus ammonia. Cause community acquired ammonia. What is beta hemolytic? Streptococcus pyogenes, cause strep swells. What is gamma hemolytic? Enterococcus facilis. Okay, those are the good examples. Look at here, you will see they grow dramatically. When you see alpha hemolytic, dark green color, it's Streptococcus ammonia. Streptococcus pyogenes, it is a little bit like how we say, a little bit like a dark red colony in the center, but you see it's transparent surrounded. It will be more obvious when you see something in the lab. Okay, so that's alpha and the beta difference. Okay, these are the key. Now we're gonna say something. It's a little bit easy. We will practice on Tuesday. Isolation pure culture. So how are we going to isolation pure culture? It's coming from Bob Koch using agar medium, and we are going to get our pure culture from a single colony. So we do spread plating, strict plating, and pore plating. But I want to tell you one thing. This sentence here a little bit misleading. We basically, realistically in the lab, we using strict plating is to see the presence, absence of a bacterial colony. So which means presence, absence of bacteria. And we use spread plating and pore plating to numerate the bacteria, which means how many bacteria are there. So spread plating and pore plating, we will get pure culture, yes, but we are not purposely to do it. And we will practice on Thursday, and you will know why we don't use it purposely, because it's very time consuming and lots of labor there. And the strict plating we did on last Thursday, it's very easy. Is that right? Okay, so those are the things we want to talk. Okay, strict plating we already practiced in the lab. You remember, we are getting a loop picked from a stock culture, very intensive streak at the beginning. Then we flame the loop, do a second charge, and from the side to do a third charge. Then we flame it again to the fourth, then to the fifth. Now basically here the picture they did the fourth, and in the lab I usually ask you to do the third charge. And we will look at Thursday to see whether you get a single colony. And I said very simple. this is a serial dilution on solid agar. Is that right? Because from the smear here, lots of colony, you cannot differentiate there. After strict plating, you get a single colony. That indicates a pure culture. Okay, that's strict plating, we already did. Now, spread plating and pour plating. I will just briefly mention here, we'll practice Thursday. Basically, is the bacteria. We're going to go through a serial dilution, which is 10-fold or 100-fold. Then spread plating, we use hockey stick to spread on this agar surface. And pour plating, we are pouring a bacterial medium there. And that is melted agar, which is about 50 degrees Celsius. So spread plating and pour plating, what's the difference? Some heat-sensitive bacteria might be killed by pour plating because pour plating comes from the medium, has melted agar, which has mild heat there. And spread plating from the agar plate is prepared, pre-melded, which is already solidified. Now the next question is the bacteria agar there, you pour, you spread the plating, you see the colony there, like this, for example. Then how do you know it's countable? How do you know it's uncountable? We gave them a range, which is 30 to 300 cells, we think it's countable. Less than 30, we usually say it might be coming from cross-contamination. More than 300, that could come from too much. Is that right? It's not going to be numerable, reasonable to count. Maybe I messed it up, everything. So we gave them 30 to 300 is acceptable legal zone for bacterial colony. Now this is what the result looks like for spread plating and pour plating. Can you see also a single colony? Is that right? Compared to strict plating, is that the same as single colony? But we are not supposed to say we isolation bacteria use this method. And this is for numeration. We want to know how many it is. Okay? This is the one we will do in lab. We're using 9 ml tractic soil broth, or we're using buffalo peptone water, or maybe 9.9 ml to do a 10 and 100-fold serial dilution. And finally, we get a colony on the plates after incubation. And I'll show you in the lab in more detail, because when we talk here, it's a little bit confusing. We're going to practice this in the lab. Just let you know, this is going to be the similar thing you do in your chemistry lab, practice a 10-fold. And we basically do a 100-fold serial dilution. So the same knowledge, you can go ahead to review your chemistry lab. It's very similar. Some of you never figured out the 10-fold serial dilution, what's the story behind that. Some of you are very good at the math, and you can figure it out very easily. Okay, just want to give you some hints. And I'll have another fact sheet on Thursday show you how we do this detail, and some quiz questions for you to practice. Next, I want to just briefly tell you, in the lab what I worked before, we had a spiral plating. This machine is very expensive, $25,000 to $40,000. Why we use this? This will cover more dilution factors, which means you don't have to do so many dilutions. It's covered like 10 to the 0 to 10 to the 4th. So there is, this one is like a bumper at the back. The first one is alcohol, you clean it. Second one is water. The third one is also water clean. So alcohol, water, water clean. Then this is the pipes. The pipes will be absorb the liquid. Then after each sample, it will be cleaned from the beginning. Then you have stirring, spin on the surface. It will do a stir. This is use crystal violet to do a demo. You see all the circles there, like a target. This is after incubation. You see the colonies spreaded. There is no way you're using eye to count it. Usually, let the machine read it. Okay. Now the question is why we use spread plate, spiral plate. This is used to widely to testing some of the liquid samples. Spiral plating is not good for food sample because food sample has lots of the food dust and the food particles will stuck the pipes. So only liquid sample, like not like those purple orange juice, maybe a thin juice or like purified juice or lemonades or those things. Using to testing, maybe wine is fine. We can test the bacteria from the liquid samples. Okay. I would say the good thing is save some labor, save some of the dilution tubes. But it's not quick. There's one sample taking like 2 minutes to do. It stirs very slow. Just to let you know, there's some fashion stuff. And this is old time. When we don't have a machine, what are we going to do? You're using those cards to put it there. So you do a manual calculation. Okay, here is something. We talk about coxair, rods, vibro, all those. Remember, those we call cell morphology, which is a bacteria cell morphology. This slide here tells you is a colony morphology on an agar. I'll give you a chance to practice next week when we do a mixed culture of Micrococcus and E. coli. You will see a two different type of the colony. So what are they? Their morphology could be punctiform, circular filaments. The elevation could be flat, raised, or convex, and the margin could be lobate, erodes, curved. I will say, somehow, they tell you something. So for example, Micrococcus is a little bit yellow. E. coli is colorless. Neisseria gonorrhea on a plate. Neisseria gonorrhea is a pushable colony, and others do not have that pushable feeding. But other than that, it is hard to say which bacteria is which based on only the colony morphology, but they give you some of the basic information. Okay, so we don't mention this too much, just give you one time to practice. Compared to the cell morphology on a glass slide, this one is less used. So just let you know a little bit. Okay, how are we going to measure microorganism counts? There is several methods we can do. First of all, directly counting colonies on other plates. We will practice in the lab. The second one is in the other time, we can using a chamber. That's called, there is a terminology for that called Petrov-Hoffby counting chamber, which means you have those well, have a chamber, you put a bacterial solution there, then you cover glass slides, then you lock those